Welcome to the online causal inference seminar. Today, we're excited to have Wang Miao from Peking University, who will talk about introducing the specificity score, a measure of causality beyond p-value. As usual, during the talk, please submit your questions via Q&A. Today, we have Sarah, who will help out and who will bring the questions to our speaker. After the talk, we will have a discussion by Qingyuan, who's also an organizer, as you know, so we're also looking forward to that. Now, without further ado, let's get started. So, Wang Miao, whenever you're ready.
Yeah. All right. Okay. Thank you, Dominic, for introducing me, and thank you for inviting me to give this talk. I'm very excited to be here and to share some of my recent work. So first, let me give an overview of my research. My research interest in methodology for causal inference and missing data, data fusion, and their applications in observational studies. So observational study often an important data source for scientific research, but manipulation of research subject is not allowed in observational studies. So unmeasured confounding, non-ignorable missing data, and heterogeneity often arise, and they may impact and possibly invalidate the causal inference. So to mitigate these challenges and to improve reliability of causal inference, I have been developing novel methods for confounding adjustment, non-ignorable missing data, and data fusion. I have been devoted to application of these methods and collaborative research in test and design, vaccine effectiveness, gene expression study, and so on. So today I'm going to introduce some exciting work I recently worked on. It is called the specificity score. This work aims to develop a measure of causality in observational studies. It is closely related to recent debate on the use of p-value in scientific research. I will discuss the underlying reasons behind the p-value crisis from the causal perspective, that is the adjustment of a confounding bias. I will introduce the specificity score for confounding adjustment, and I will illustrate with the mouse obesity example. And in the last, I will discuss the connections to heal the specificity and the other methods. So p-value in scientific research, p-value is used as a central tool for scientific discovery. We all know p-value very well and frequently use p-value in our own research. But there is a lot of debate on the use of p-value, particularly in 2018, the journal Political Analysis decided to banish the use of p-value. Political Analysis is an influential journal in political science. This announcement caused a lot of debate in statistics and science. Then later we saw this comment paper in Nature. Scientists rise up against statistical significance. One of the three authors is our familiar epidemiologist, Greenland. And this paper received more than 800 signatories from scientists from different areas. In fact, the journal in public health, the journal AJPH and epidemiology has a long-standing policy of discouraging the use of p-value since Rossman was the editor in 1990s. There are also a lot of discussion on the reproducibility and the publication bias, which are related to p-value. Several other journals also banish the use of p-value, but they cannot find a better substitute and finally remove the ban. I had a look at the guideline of political analysis a few days ago. The journal now allows authors to report p-values again. Researchers also suggest the supplement and the replacement approaches for p-value. such as confidence interval, effect size, and Bayesian methods. And big names in biomedical science recommend lowering a p-value threshold from 0.05 to 0.005. These proposals somehow calm down the debate on p-value in certain areas. But the challenge for p-value, or more broadly for statistical significance, remains in scientific research. One of the biggest reasons is that statistical significance does not mean causality. P-value measures the extent to which the observed association is attributed to random error. But in the data collection process, there exists systematic bias. So the observed data law is a complicated consequence of the underlying causality, the systematic bias, and random error. So p-value by definition is about sampling error, not bias. If the bias is identified in advance, one can use p-value to assess whether the association in data is due to causality or chance. But otherwise, one cannot distinguish causality from bias. So what bias may arise in scientific research? Confounding bias is a major one. There exist other kinds of bias, such as selection bias, measurement error, and other bias. These kinds of bias are somehow related to confounding bias. And in this talk, I will focus on confounding bias. So let X and Y denote the treatment and outcome of interest. And U is a common cause of X and Y, which is called a confounder. If U is not observed, then the marginal association between X and Y will be biased from the true causal effect. This is called the confounding bias. So, for example, sex is an important confounder in scientific research. So suppose in a mouse study, if most females are assigned to the control group and most males are assigned to the treatment group, then the group difference, then one cannot distinguish whether the group difference is due to treatment or sex. So in many studies, researchers need to control or adjust for sex, and similarly, age and other baseline covariates. But in observational studies, it is not easy to control or adjust all the confounders. Gene expression is such an example where batch effect is widespread. In gene expression studies, we are interested in how the gene expression affect physiological traits. But the measurement of these variables are under different processing batches, such as different processing such as different laboratory conditions, different personnel, even different data and time. These different processing conditions also have also affect the gene expressions. So batch effect is an important source for confounding in genetic studies. So this question can be formulated as multi-treatment, multi-outcome causal inference with unmeasured confounding. Let X denote a vector of K treatments, Y denote a vector of P outcomes, and U denote an unobserved confounder. For example, X is the gene expressions, Y is the vector of physiological traits, and U denote the batch effect. Our goal is to test the effect of X on Y. In particular, I will focus on testing the effect of X1 on Y1, given the confounder and the other treatments. And the testing for other effects will be similar. Here, X1 bar denotes the other treatments except for X1. Note that this is not a usual hypothesis testing problem. the challenge here is that U is not observed. So for simplicity, I will use the linear model to ground ideas. Here, beta is a matrix capturing the effect of X on Y. Alpha is a vector capturing the confounding effects of U on Y. Here is a graph model for illustration. We allow for additional confounding within X and additional confounding within Y. So from the observed data, we can obtain the regression coefficients gamma by regressing Y on X. But gamma is a mixture of the true causal effect beta and the confounding bias delta times alpha. Alpha is a confounding effect of U on Y. Delta is a regression coefficient of U on X. Delta times alpha is a confounding bias. So without additional information, we cannot identify beta from gamma due to the presence of confounding bias. So researchers have developed a variety of successful confounding adjustment methods. The instrument variable is widely used, and the recent progress in local treatment effect won the 2021 Nobel Prize in Economics. And IV is a statistical basis for Mendelian randomization in epidemiology. MR uses gene variants as the instrument variables to identify the causal effects between different phenotypes. But in practice, it is not easy to find an instrument variable because the instrument variable may also be confounded and it may have direct effect on the outcome. And recently, we developed a negative control proximal inference approach in a series of work. The negative control method requires a negative control exposure and a negative control outcome. The negative control exposure is required to not directly affect the primary outcome and not directly affect the NCO. And the NCO is not directly affected by the primary exposure and not directly affected by the NCE. We have applied this the negative control method can be viewed as a generalization of the IV method because the NCE now is allowed to be correlated with the confounder. We have applied the negative control method to the evaluation of COVID-19 vaccine effectiveness and EHR study, air pollution, and other real-world problems. And this line of research is part of work that one senior collaborator, Eric Checkin, the 2022 Russell Prize for Statistics. So in addition to using auxiliary variables, researchers in genetics and bioinformatics develop a variety of confounding adjustment methods. A class of such methods can be summarized as the linear factor model approach. For the instrument variable negative control factor model approach, we need to know the auxiliary variables or the independent structures between the study variables. But in practice, it is not easy to have such prior information. We do not know whether the causal effects exist or the independence between the study variables. So sometimes it is only plausible to have a rough idea on the broadness of causal associations. Let me give an example. In EHR studies, we have patient records on multiple treatments and multiple diseases. So a medicine may be effective for several diseases, but it is unlikely to be effective for many diseases. So how can we use this information on the broadness of causal effects to make causal inference and to adjust for confounding? So recently in this paper, I describe a specificity analysis framework that leverages this idea to adjust for confounding. So I propose a causal specificity assumption. The first term of this assumption says y1. So now we just focus on the effect of x1 on y1. So the first term says y1 is directly affected by at most k-star treatment. And then the second term says x1, xk as a vector can directly affect at most p-star outcomes. So here, k-star, p-star represent the restrictiveness of the assumption. As the larger k-star and p-star, the less restrictive is this assumption. The existence of IV is a reflection of causal specificity. But here we do not need to know. But here we only require a loose upper bound for the number of active causal effects. We do not need to know exactly which causal effects exist or not exist. So a sufficient condition for 2 is that each treatment can directly affect at most p star over 2 outcomes. So I call this assumption causal specificity. It is related to Hill's specificity criterion. In 1965, Sir Austin Bradford Hill offered 9 viewpoints on causal inference in observational studies. One of them is called specificity. It means the less broadly an exposure is associated with the outcomes, the more likely these associations are to be causal. Hill's specificity is very influential and is widely used in biomedical and epidemiological research until today. But there is also a lot of debate on this specificity criterion. So literally, Hill's specificity is about observed associations. So it is unlikely to hold in real world because confounding may introduce correlation between everything. In contrast, the causal specificity is about the reality of unknown causal effects. It is not about the observed association. So the justification depends on domain knowledge, but not on observed associations. So how can we leverage this causal specificity assumption to do confounding adjustment? Let me give you some intuition. So recall the regression coefficient gamma is a mixture of the true causal effect beta and the confounding bias delta times alpha. Without additional information, we cannot identify beta. Suppose now we know that xk, yp are a pair of valid negative controls for x1, y1, like in this figure, in this graph model. That is beta k1, the causal effect beta k1, beta kp, and beta 1p are equal to 0. Suppose we have such information. Then we immediately obtain this result. So define lambda kp by this formula. It is the ratio of some regression coefficients, the corresponding regression coefficients. Then it is easy to verify that lambda kp will be equal to delta 1 times alpha 1, which is exactly the confounding bias. So, but in fact, we do not know which variables are valid negative controls. So we just try all xk and yp and compute all the lambda kp's. Some of them are computed from valid negative controls, but some are not. We do not know which. However, the causal specificity assumption tells us we have at least such many valid negative controls, and all the corresponding lambda kp's should be equal to delta 1 alpha 1. And further note that under the null hypothesis of no causal effect, there is a question on slide 16.
Do you want me to read the question?
Yeah, on slide A16, the edge between Y1 and YK is for the spurious correlation due to U. Okay. So you mean this edge, right? So this edge here I draw it. It is not a direct edge. So it means let me go back to the it means the confounding within Y, right? It means the confounding within Y. Okay. Let me move on. So okay. So I just said so under the null hypothesis of no causal effect, all such lambda kp's are equal to gamma 1 because under H0 gamma 1 is completely a result of confounding, and gamma 1 should be equal to delta 1 alpha 1 the confounding bias. So under H0, such many lambda kp's should be equal to gamma 1. So this theorem summarizes what we obtained in the above argument. If H0 is correct, then at least such many lambda kp's are equal to gamma 1. Note that the regression coefficients and thus lambda kp's can be computed from the observed data. So we can test H0 by assessing how many lambda kp's depart from gamma 1, because all the lambda kp's gamma 1 gamma kp can be computed from the observed data. So this theorem provides a testable implication of H0. So motivated from this result, I propose the specificity score. So we rank all the lambda kp's from the largest to smallest, and let Q1 be the proportion of lambda kp's that are strictly larger than gamma 1, and Q2 the proportion of lambda kp's that are strictly smaller than gamma 1. Then the specificity score is defined as the maximum of Q1 and Q2. So by definition, the specificity score measures how extreme gamma 1 is when compared to the lambda kp's. So note that lambda kp's can be viewed as the estimation of the confounding bias. So a larger specificity score means gamma 1 is very different from lambda kp's. That is, gamma 1 is very different from the estimated confounding bias. That means the observed association cannot be explained away by confounding. And that is evidence of causality. So in this view, the specificity score is a measure of the credibility for the causal effect of X1 on Y1. It measures to which extent the observed association cannot be explained away by confounding. So this is evidence for causality. So by definition, the specificity score is between 0 and 1. It is based on ranking, and it is dimensionless. It does not depend on the measure scales of the variables. And most importantly, the following result provides a non-trivial upper bound for the specificity score. Under the causal specificity assumption, if H0 is correct, then the specificity score is smaller than tau. Tau is defined in this formula. So this result establishes the basis for construct valid test against the null hypothesis. If the specificity score is equal or larger than tau, then we reject the null hypothesis. The critical value tau is defined in this formula. It depends on K star and P star. That is restrictiveness of the causal specificity assumption. So if K star and P star are much smaller than KP, then tau will be close to 0. And in this case, it will be much easier to test the null hypothesis. This is often the case in genetic studies where the causal effects are very sparse. So here is a summary of the entire procedure. So given n observations of x and y, we first obtain the regression coefficients gamma, kp. Then we estimate the confounding. Then we estimate lambda kp using the regression coefficients, and estimate q1, q2, and the specificity score by comparison between lambda kp and gamma 1, 1. Here, this rate of term is included to account for sampling error, because here I assume that a gamma kp can be estimated in a rate of square root n. And in last, we can use the specificity score to test the null hypothesis. Tn equals 0, Tn equals 1 means to reject the null hypothesis. We have some theoretical guarantee for the test. So suppose the regression coefficients can be estimated in square root n rate. Then the specificity score estimator is consistent, and the test is valid with type 1 error controlled. The test may not have power for all alternatives, but the third result says if the true causal effect is beta 1, 1 is large enough, then the power will approach 1 as the sample size increases. This is consistent with the epidemiological practice that a large causal effect is more likely to be detected. So this is for testing the causal effect of X1 on Y1, and we can replicate the procedure to test the effects for other Xi, Yj, but we need analogous causal specificity assumptions for Xi, Yj. So to communicate all the testing results in a universal and efficient manner, it is better to consider a visualization approach. I will use this numerical example to illustrate. So suppose 5,000 samples of 5 treatments and 8 outcomes are generated from this model. It is just a simple linear normal model, but here sigma x and sigma y can be arbitrary. So it allows for dependence within x and dependence within y. That is confounding within x and confounding within y. In this setting, the last zeta value is set 2. It is a large value. That means strong confounding on x5. So this represents a typically difficult situation in scientific discovery, where strong confounding may introduce false discoveries. The true value of the causal effects are specified in figure A. So we first use the regression coefficient and p-value to detect the causal effects. The regression coefficients lead to substantially false discoveries, particularly for those accompanied with large confounding, as shown in the last row of figure B. And the p-value is computed from the regression coefficient and its variance. The performance of the p-value is even more disastrous. It has a lot of false discoveries because the confounding makes the correlation between everything significant. But the specificity score and the specificity test can recover both the both the active and the null effects very well. In this setting, with the correct critical value, that is tau equal to 0.71. If we want to be more robust, let the critical value increase to 0.96. Then we only detect a subset of the causal effects. But now we have high confidence about these 5 effects, and we have high confidence to claim they are causal. This is for one simulation. And I further replicate 1,000 simulation and compute the power of the test. The specificity test can control type 1 error very well. But the p-value based test lead to a lot of false discoveries, as shown in the last row. So based on this result, one may argue that p-value may be still useful for screening effects because a p-value seems to select a larger set that contains all the active effects in this example. There's one question: could e-values also be alternative for p-value here? So here I didn't discuss the e-value. So based on my understanding, so I think you mean the e-value by Peng and Tyler Wang Miao, right? So based on my understanding, e-value is a transformation of the observed association, like a risk ratio or something. So it is a transformation of the observed association. I think it should not introduce additional information additional information other than the observed association, right? Yeah, there are a lot some discussion on the connection of e-value and the p-value and the application of e-value in causal inference. But here I think it is different. Okay. Okay, based on this result, you may argue that p-value is still useful because it seems to select a larger set of causal effects. Unfortunately, this is not true. So consider the same setting as in example 1, but now the zeta3 is set 2. In this case, the causal effect of x3 on y5 cancels with confounding. So the observed association between x3 and y5 will be very weak. This represents another difficult setting for scientific discovery, where a strong causal effect may be overlooked due to weak correlation. So I replicate 1,000 simulations under this set. So the specificity test can control type 1 error very well, but the p-value test makes a lot of discoveries, but just ignore this very strong causal effect of x3 on y5. So p-value, there is no guarantee that the p-value can select a larger set of causal effects. So some authors recommend lowering threshold for p-value. This may be helpful to reduce false discoveries, but it is more likely to ignore active causal effects. So far, we have developed a specificity analysis framework, including a specificity score, measuring the credibility of the causal effects, and a specificity test for detecting active causal effects. All these tools require the causal specificity assumption. So this assumption may be violated in practice. One may argue that the causal relation may exist between everything. So you may have such belief. For example, smoking causes a lot of diseases. So I totally agree, but my argument is that not all causal effects are equally important. Some causal effects are large and important, and the others are small and trivial. So smoking increases the risk of lung cancer by 9 times. This is a very large effect. But the increase in coronary disease is no more than twice. It is a small effect. Although this small effect compromises the validity of causal specificity, it should not impact the influence on the larger effect on lung cancer. So I further formulated this idea with the weakened causal specificity assumption. It allows for small causal effects everywhere, but restrict the broadness of large causal effects. This is consistent with the goal of scientific research. Our goal is to detect some large and important and meaningful causal effects so that we can base on them to make decisions or policies. such large and important causal effects must be relatively rare because we are trying hard to find them. So as long as you are studying a causal effect, you have implicitly assumed such effect, such assumption. So the meaningful causal effects are relatively rare. So here eta is a user-specified threshold or sensitivity parameter for a meaningful or interesting causal effect. So the smaller eta means a stronger assumption. If eta equals 0, then the assumption reduced to the previous strict version. For example, we observe heavy drinking can increase blood pressure by 10. We suspect that this may be due to confounding, and we believe a causal effect larger than 1 is meaningful. So in this case, eta equals 0.1. So what we should do is to conduct a specificity test and the different values of eta. For each eta, we can similarly define Q1, Q2, and the specificity score. And we can show that the specificity score still have this upper bound tau. The bound tau is the same as before. And based on this inequality, we can construct a value test against H0 and the different values of eta. So in practice, we should conduct a specificity test by increasing eta from 0. If a causal effect remains through all the tests, then we have high confidence to claim that it is causal. So back to the numerical examples. Now I add some perturbations to the first row and the first column of beta. And I conduct a specificity test and the different values of eta from 0 to 0.4. As eta increases from 0 to 0.4, the type 1 error of the test attenuates toward 0. For example, this one. But the power for some effects, the power for beta 3.5 and beta 5.7 disappears. And finally, we obtain these 6 effects in this figure. Then we have high confidence to claim that these 6 effects are causal. We have high confidence. There's one question. Do you have any asymptotic results for the test statistical specificity score? Yeah, I just go through the results. That is this theorem. So this theorem says the specificity score estimator is consistent and the test is valid with type 1 error controlled. And under certain situations, the test has power approaching 1. Yeah, this is the asymptotic results for the test. Okay, this is for example 1, and similarly the results for example 2. I will skip. So so far we have established the specificity analysis and the linear model. The linear model will no longer be suitable for complicated situations. In this case, it is better to consider a non-parametric model. The following model is referred to as the non-parametric model, where MP is unknown and unrestricted. The idea is to apply the confounding bridge functions we proposed in previous negative control work to characterize non-parametric and non-linear confounding effects. And we can obtain similar results to those under the linear model. And I will skip this part and we can discuss later. And we can also achieve identification of the causal effects, but under a stronger causal specificity assumption, like this one. It has more restrictive constraints on the broadness or causal effects. And we can also allow for multivariate confounder. If we know the dimension of the confounder, we can select more variables for negative controls. The idea will be similar, and I will skip the details. So I will apply the framework to a mouse obesity study. The data set I use include 248 observations on 9 SNPs, 17 gene expressions, and 17 physiological traits, including length, sex, and 15 traits that are relevant to metabolic syndrome and obesity. Here is a table for such variables. And our goal is to investigate the effects of the gene expressions on the physiological traits. So we first apply the linear regression. The linear regression detects very dense effects, but we suspect that they may be a consequence of unmeasured confounding, because unmeasured confounding often arises in gene expression studies due to batch effects. Then we apply the IV method by using SNPs as IVs. The IV method detects quite a fewer effects. And then we apply the specificity test and the different values of eta. The specificity test detects less dense effects than OLS, but more effects than the IV method. And the specificity test indicates that these 5 variables, Y12 to Y15, is unlikely to be affected by any of the treatments. So we can use these 4 variables as negative control outcomes and use the IVs as negative control exposures to do a negative control analysis. And the negative control method shows less dense effects than OLS. So some of our findings are consistent with previous biological studies. Sex makes a big difference in body adiposity index, which is defined as the fraction of fat in weight. This is due to the difference in body. This is due to the difference in body composition between females and males. And the gene SOCS2 has a negative effect on leptin. This is because the overexpression of SOCS2 can inhibit the expression of leptin receptor. And the gene APOA4 can elevate the level of cholesterol. This is because fat absorption can stimulate intestinal APOA4 synthesis. This is well accepted in biology. And by using specificity test, we show these above gene traits associations cannot be completely attributed to confounding. There exists some causal mechanism behind these associations. Although false discovery may present due to violation of assumptions of models, and further biological experiments are required to verify these results. In summary, we propose a framework for specificity analysis, including a causal specificity assumption and characterizing broadness or causal effects, a specificity score measuring credibility of causal effect, and a specificity test, and a sensitivity analysis approach. And identification and estimation and generalization to non-parametric model are also available. So the notion of specificity, the notion of Hill's specificity does not get much respect in nowadays causal inference. And many authors consider specificity invalid and misleading. So this work may not be considered as a renaissance of Hill's specificity, but we help to explain 3 long-standing questions that are fundamental to Hill's specificity. So the first is, what is underpinning causal assumption for specificity and whether it is plausible. Second, how to measure specificity in observational studies. We propose the specificity score. And third, how to use the specificity measure to test the causative hypothesis or identify causal effects. We propose the specificity test and the identification and the estimation methods. And we also clarify the connection between specificity and the IV and the negative control methods. There are some favorable properties of the specificity analysis framework. So compared to IV or factor model, we do not need to know the auxiliary variables or the independence structures. And it can be used to resolve the invalid IV problem and the selection of IV, which I didn't talk in this talk. P-value measures the impact of random error. In contrast, the specificity score measures the impact of bias. So this is essential in big data, because as the data size increases, the impact of random error will disappear, but the systematic bias remains and will dominate random error. For scientific research, large sample size is preferred, but large sample size tend to produce small p-values. And the small p-values may lead to trivial scientific findings that are in fact meaningless associations. This is a crucial question in big data analysis. We have too many small significant p-values, but many of them are in fact trivial findings. But for the specificity score, large sample size leads to better estimation of the specificity score. And larger associations are also preferred in scientific research. But I should caution that large association does not necessarily mean large specificity score. And contrarily, a small association may have larger specificity score, as we show in the numerical example, in example 2. So this may be helpful to reduce publication bias. Also, there are some limitations. The framework is best suited for multi-treatment, multi-outcome causal inference. And for single treatment and single outcome, it may not be straightforward to apply. And the framework is a robust and sometimes conservative framework. It may lack power in practice. And we have assumed that we know the confounder dimension. In practice, it is of interest to determine the confounder dimension adaptively. The framework is readily to extend to other problems. For example, other bias, selection bias, invalid IV issues, measurement error, and to high dimensional settings so that we can handle large scale data. In addition to the gene expression study, the framework has potential application in EHR data, multivariate Mendelian randomization, and other real-world problems. And that is all my talk. And thank you. I'm happy to take your questions.
Thanks for the very nice talk. I think there's one question. Sarah, do you want to take that?
Sure. So the question is, could you... Oh, sorry. You can read it, yeah.
Okay. Okay, let me first respond to the question in the QA. Could the specificity score be used to assess causality in any causal model of potential outcome or graphical type, say in differences or PAG or MAG? So I think it's possible because there are some equivalence between these causal models, right? There are some equivalence between potential outcome and graphical models. So although I didn't consider graphical models or other type of models, I think it's possible to generalize or adapt to such models because these causal models have some equivalence. Yeah.
Awesome, thank you. So I think, yeah, in the interest of time, we should switch over to discussion. Qingyuan,
Okay.
whenever
So
you're
I
ready.
should stop share, right?
Yeah.
Okay. Hi, Qingyuan.
Hi. Okay, thank you very much for the very nice talk. I mean, I'm always a great fan of your work. I think it's fair to say that Miao's work on negative controls has changed how many of us think about specificity. I find it actually more useful to think about specificity or negative control than proximal causal inference, which is my understanding is that that's kind of like a more recent rebranding of a similar methodology. At least I find it more useful conceptually to talk about specificity. So Miao gave a nice review of specificity, which is one of the 9 criteria for causality given by Bradford Hill. And this is also one of the most controversial criterion of Hill's, because it turned out that specificity does not quite work for smoking, the exposure that pretty much motivated his list. So the reason why I prefer to think about specificity or negative control is that this is actually a very basic experimental technique that's can be widely found in all areas of science. And as Miao pointed out, this is not adequately considered by theoreticians so far. My understanding of this concept is graphical. So causal specificity or negative control basically means a lack of certain directed edges in your graph. And in some sense, this is basically the only tool we have against unmeasured confounding. And Miao nicely summarized several problems. For example, how instrumental variables can be thought as a special case of sort of specificity-based causal inference. So Miao started his talk from the replication crisis and p-values. So he cited this paper by Wasserstein and Lazar. It's titled "The ASA Statement on P-Values" in American Statistician 2016. I, for a long time, also thought this is the kind of the official statement, but it turned out later that I heard from a talk by Joao Benjamini that this is actually not the official ASA policy. There's another paper published in 2021 from another eminent group of statisticians. They concluded p-values and significant tests, when properly applied and interpreted, increase the rigor of the conclusions drawn from the data. So, so my point with this is just that maybe we shouldn't completely abandon p-values. But in my opinion, the p-value is also the wrong culprit in this whole debate. There are more significant and difficult issues, including selective inference and causal inference. So for the rest of the discussion, I'm just gonna sort of try to ask some questions, which I think are about lurking issues that are sort of behind Miao's talk. The first issue I found was that there's this assumption that there seems to be one unmeasured confounder that has uniform effect across sort of all the treatments and outcomes that we observe. So my question to Miao is basically, are these assumptions true or important in the methodology? The second issue is that in some sense, at least the linear model that Miao spent a lot of time on, that was based on a latent variable model. And arguably, there's a natural alternative to the specificity score, which is you try to model the low-dimensional confounders. So I wonder if you have compared specificity score with other sort of model-based approach that assumes like a low rank plus sparse type of structure. Related to that, I think as bad as latent confounders are, they in some sense point to otherwise unknown causal mechanisms that could also be interesting for other purposes too. And one example is latent mediators. And in the sort of genetic studies, this could be mediators between multiple sort of genetic biomarkers and sort of complex traits, where in this case, a similar sparse plus low rank structure may show up. So my question to Miao is, can we distinguish latent confounders with latent mediators without background knowledge? The third lurking issue, which is kind of related to the origin of this whole idea about specificity, this is before Bradford Hill gave his list of criteria. In the 1950s, when there was this big debate about smoking and lung cancer, there was a criticism of the study by Zhao and Hill by a physician called Joseph Bergson. He basically argued that if you look at this data that was originally reported by Zhao and Hill, and if we look at risk differences instead of risk ratios, then this association between lung cancer and smoking isn't too specific. If you focus on this last column, this is actually not even the largest compared to, let's say, this heart disease, basically. And this is one of the reasons why specificity didn't quite work for smoking, because smoking is a cause for a lot of diseases. But basically, Bergson's point was that sort of Zhao and Hill focused maybe too much on risk ratio as the effect measure instead of other potential measures. So the argument of specificity was not, it seems that it is perhaps tied to some choice of effect measures. I think this could be especially relevant if we consider this weakened notion of specificity that Miao described. So I just wonder if Miao has any thoughts on this. Thank you. That's all from me.
Thank you, Qingyuan. Thank you for the insightful comments and the question. So can you go back to your first, I think first slide. I want to respond from your first slide.
From here?
Yeah. Yeah. The first slide. Yeah. Here. So so in your second term, you said Hill's criterion is motivated from smoking study, but specificity does not work for smoking. So if you account for the magnitude of association, it does work. So I just mentioned the example of smoking. I said smoking increases the risk of lung cancer by 9 times, but the increase of coronary disease is no more than twice. So this is from Hill's paper. This is his argument for smoking, and it is also the argument in the U.S. I think in 1964, the 1964 report on smoking on lung cancer. So if you consider magnitude, it can be viewed as some specificity, and I just in my talk, in my work, I formulated this idea as a sensitivity analysis approach. So weaken the causal specificity assumption that we allow for many small effects, but restricted the broadness of large causal effects. So suppose smoking causes lung cancer, has a large causal effect on lung cancer, but smoking may have relatively small effect on other diseases. In this case, it may be useful to use the specificity analysis to make a causal inference on smoking on lung cancer. And
okay. You want me to put another slide?
Yeah. So the magnitude of association matters. Yeah.
Yeah, this one.
Yeah. And your second, your first question, first the issue.
Okay.
Okay, you want me to talk about the last slide, right?
Either way, yeah, whichever you want.
Okay, let me go one by one to your first issue. So consider the dimensional confounder So yeah, I do assume that the confounder is known. It is not necessarily one dimension. It can be multi-dimensional confounder. Although in my presentation I use one dimension confounder, but I said it can be generalized to multivariate confounder. And the generalization is quite straightforward because in the construction of the specificity score, I use each x, k, y, p to construct the specificity score. So if you have multivariate confounder, you just use multiple x, k, and multiple y, p to construct the specificity score. It is straightforward, but we still to know the dimensional confounder. So my last question in my talk is that we need to determine the dimensional confounder in practice adaptively. I'm not sure if the specificity analysis can do this. It remains to study in the future. Yeah.
Okay.
And then next. So talking about mediation and confounding. So latent mediator and the confounder. So suppose the confounder and the mediator are all observable. Can you distinguish whether the variable is a mediator or confounder? No. Even all the variables are observed, you cannot determine which variables are mediator or which variables are confounder without additional assumption. Because they are Markov equivalents, you cannot distinguish them. So this is my response to your Q2 tool. You cannot distinguish latent confounder and latent mediator.
That makes sense to me.
Yeah. So go back to your Q2 1. So there do exist some work on low rank plus sparse models. But my sense is that most of this work concerning sparse structures are accompanied with high dimensional settings with other conditions or assumptions. And the other conditional assumptions that are related to some causal structures. I think it's just it is just not merely low rank plus sparse. It should have some other conditions to guarantee estimation or identification in such works. So I currently do not have a direct comparison between these two frameworks because the condition assumptions are quite different.
Okay.
So talk about so you mentioned one of your paper, right? Yeah, the last slide.
Yeah. You want to keep on?
Yeah. The paper by Gao, right? Gao
Yes.
et al. I just have a quick look at the paper. If I understanding correctly, so this paper assumes that all the effects from X to Y are through some mediator, right? Some low dimensional mediators. So that means you do not have other direct effects from X to Y. So I think this is quite a different setting from what I consider in the talk, right?
Okay.
Yeah. Okay. So I
this
consider the confounding problem. So there are two paths from X to Y. One path is direct path, and the other path is the backdoor from the confounder. So I think it's different from the paper you mentioned.
Yeah, I'm wary of time constraints.
Okay.
So you've responded to my last.
Yeah. Okay. 1 minute. Yeah.
So yeah, let's just let the organizers and then
okay.
we can.
All right.
So you mentioned so you mean in the
Yeah,
so you mentioned in the risk difference scale sorry?
Can you just 20 seconds for your last answer, and then we'll have to quickly wrap up. Is that okay?
Oh, in my last answer, right?
Yeah.
So my last answer is that I do not agree with the with the method that you consider specificity in your last slide. That is the style of prepared for the Hill's specificity. It is different from my consideration of specificity and my specificity score. It's different. Yeah. So that's my last word.
Great. Thank you.
So we
Thank
can talk about the details when you have time.
Yeah, sorry, we're just running. We're over
Sorry
time.
about it.
So yeah, first of all, thank you so much for a super interesting talk, Wang Miao, and for a nice discussion,
Thank you.
Qingyuan. So this was the last seminar actually for this year. We're now going into the summer break. So I hope you all have a great summer, and then yeah, see you all back in fall. Thank you all. Have a great summer.
Thank you. Bye. If you have any question, you can email